Okay, welcome back everyone. So in this section, we're going to talk about an introduction to probability. And you're going to see why probability is going to be useful in this randomization process when we're going to utilize hypothesis testing. So previously we did hypothesis testing and we did it by experimentation. And it turns out that you could actually use probability and avoid having to do a numerical simulation on the computer to actually do hypothesis testing. So based on that, we're going to need some background in probability. A lot of this will be review for most students, but it's worthwhile to go through to reinforce our knowledge of it. Okay, so a random process. What is a random process, right? Well, we have the definition written down. And so basically it's a situation where we know that which outcomes could happen, but you don't know exactly which one's going to happen. So we know all the outcomes, but you don't know which particular outcome will happen, right? So for example, if you toss a coin, we know the outcomes are going to be heads or tails, but at a given toss, we don't know the exact outcome, right? So on toss 1 versus toss 2 or versus toss 3, we don't know if it's going to be a heads or tails on any of those tosses. We just know that it can be a heads or tails, but we don't know exactly which one it's going to be. And so that's going to be an example of the random process. So it could be a coin toss, rolling dice, iTunes shuffle, cryptocurrency prices, whether the price is going to go up or down on a given day, stock market as well, right? Prices of individual stocks or securities, whether they're going to go up or not. And in general, you want to model these things utilizing random processes, and then use probability to describe, right, the likelihood of a given event. All right, so let's look at probability, and there's lots of different interpretations. But in general, a guideline is going to be the following. So if you have an event A, that could be like, if you do a coin flip, A is going to be the event that you flip a heads. Then P of A is going to be the probability of that event. And notationally, it looks like this. It looks like P with round brackets rounded in A. That's the probability of event A occurring. So what's the probability that you flip a heads, right? For example, where A is going to be the event that you flip a heads. And in this case right here, in general, probability of a given event is between 0 and 1. So 0 indicates a probability of 0, and 1 indicates that it's going to happen almost always, right? So never happening would be a probability 0, and almost always happening will be a probability 1. Okay, and there's a couple different interpretations right here. Maybe I'm gonna skip that one. But the interesting thing to note, so frequentist interpretation, basically they say a couple things. Maybe I'll go into it just shortly and briefly, but basically outcomes, probability of an outcome is proportion. There's a proportion of times the outcome would occur if you observe this random process an infinite number of times. So if you repeat an experiment an infinite number of times, right, then the proportion that the given outcome occurs, that's divided by the number of times that it occurs, is going to give you the outcome. So basically in this sense right here, what I mean by proportion is going to be the number of times the event occurs divided by the total number of trials, right? So frequentist interpretation. And Bayesian interpretation is slightly different. It actually utilizes a subjective degree of belief. So for the same event, two different people could have two different viewpoints and assign different probabilities. And that's actually quite interesting, the Bayesian one right there, right? And they have lots of computational tools to actually show some of the results and theory from Bayesian probability. So it's a very useful framework. Okay, so let's take a look here and view this. So out of these three events right here, right, which would you be the most surprised by? So if you flipped 3 heads in 10 coin flips, if you flipped exactly 3 heads in 100 coin flips, or if you flipped exactly 3 heads in 1,000 coin flips, right? I'll give you guys 10 seconds or so to think about that. So getting 3 heads and 10 coin flips, exactly 3 heads and 100 coin flips, or exactly 3 heads and 1,000 coin flips. And it turns out getting exactly 3 heads and 1,000 coin flips is actually the one that you'd be the most surprised by, right? So getting exactly 3 heads and 1,000 coin flips. Okay, law of large numbers, the standard thing, LLN. And it basically states the following, is that the more observations that are collected, the proportion of occurrences with a particular outcome, they call it PN hat, right? It converges to the probability of the outcome. That's all it is. So the number of times a given event occurs divided by the number of trials, right? As the number of trials goes to infinity, it's going to actually converge to the given probability. That's all it is right there. That's the law of large numbers. So if you repeat a given experiment more times, then the experimental probability is going to converge to the theoretical probability. And let's take a look here. This is a fun little example using the coin flip. So if you have a fair coin, and basically if a heads comes up on each of the first 10 tosses, right? So you flip heads 10 times in a row, then on the 11th toss, right, do you think you have a better chance of getting heads again or tails or something else, right? Is it still 50%? Is it still 0.5? What do you guys think? So I'll have you guys take 10 seconds to think about that. So we flipped 10 times, we got 10 heads, we got heads 10 times in a row. Then the next flip, what's the chance of getting a heads again? Is it bigger than 0.5, less than 0.5, right? Equal to 0.5? What do you think? Put some thought into that. Okay, and here's the thing about it, it's probably still going to be 0.5. And the reason being is each toss is independent of the previous one, right? And subsequent tosses are going to be completely independent of any future or previous tosses. So that's what you can think about right here. So getting a heads on the 11th toss is the same as probability of getting a tails on the 11th toss, and they're both 0.5. So previous events do not affect the current event. And that makes sense, right? The coin is a fair coin, non-biased. And so this 10 in a row is purely by chance. 10 heads in a row, right? And one thing to state here, the coin is not due for a tails, right? You're not going to get it just because you flip 10 in a row, right? It does not actually state that you're due for a tail on the 11th toss. Something to think about. And that's kind of like a common misunderstanding of the law of large numbers, right? And they think that, random processes, they're going to compensate for whatever happened in the past. But that's actually not the case right there. It's just like the gambler's fallacy. If they think they're on a big losing streak, then they're due for a win. But probability and random chance does not care about that, right? So if they're on a losing streak, that's just going to be a random event, right? And it has no bearing on you winning or losing in the future. You may continue losing or you might win, but that outcome is independent of what's happened in the past, right? So they call it gambler's fallacy. All right, we'll talk about disjoint and non-disjoint outcomes. So these are disjoint outcome is going to be a mutually exclusive outcome, right? It means that it cannot happen at the same time. So if you say two events are mutually exclusive, they cannot happen at the same time. So for example, if you toss a single coin, it can't be both heads and tails at the same time. So those two events are mutually exclusive. A student cannot both fail and pass a class. And if you draw a single card from a deck, it can't be an ace and a queen at the same time. So those outcomes are mutually exclusive, right? And we call those disjoint. How about non-disjoint outcomes? Well, these are going to be outcomes that can happen at the same time. And so, for example, you can have a student who gets an A in statistics and an A in econ in the same semester. So that's that can always happen, right? So the event that a student gets an A in statistics, and then the event that a student gets A in econ in the same semester, right? Those two events right there, they're actually going to be non-disjoint because they could occur at the same time. Whereas if you got both an A in stats and then a B in stats in the same semester, those two are mutually exclusive outcomes. They're disjoint. And like I stated before, every time you see a concept, try to think about a specific example. Okay, let's look at the union of non-disjoint events. So what is the probability of drawing a jack or a red card from a well-shuffled full deck, right? So it's a jack or a red. So it can be so it can look at the event that you're either a jack or a red or both a jack or a red. So let's take a look at that, right? So these are all the red cards right here. And then these are going to be the jack cards right here. All right. And we're going to take a look at that particular event, right? So a jack or a red card from a well-shuffled card deck. Let's take a look at this one. This is quite interesting. So probability of getting a jack or a red is equal to the probability of getting a jack. So in this case, you're going to choose either these 4 cards right here, or you're going to choose a red card, which means you're going to choose all these right here. But the thing about that is if you choose this one plus this one, you're going to double count the red jacks, right? Because they're already included in the list of red cards. So what you're going to do is to account for that double counting, you have to subtract off the event that you are both a jack and a red, which is going to be these 2 cards right here, right? Otherwise, you're going to double count, because if you look at the event that the cards are, you draw a jack, that includes these 4 cards over here. And then if you look at the event that the card you choose is red, it's going to be chosen from these right here. But the secondary one, the event being red, is you end up choosing the red jacks twice. So you have to account for that double counting. So you have to subtract off the event that you are both jack and red. Okay, and that's the final probability is 28 out of 52. That's it you get. So probably that you choose a jack or a red, or both jack and red. Okay, this is another one. Have you guys stare at this one right here? I'll explain it, what's going on. So the question is, what's the probability that a randomly sampled student thinks marijuana should be legalized, or, keep in mind, this or is a strong statement right here, or they agree with their parents' political views. Now the or means that the student thinks that marijuana should be legalized, or they agree with their parents' political views, or they believe both that marijuana should be legalized and they agree with their parents' political views. Okay, and let's take 1 minute to take a look at this particular problem and try to analyze it. All right, I'll have you think about this for 1 full minute. Okay, I'm going to call time. All right, so if you actually guessed B, that is entirely correct. And so what ends up happening is if you go down the rows right here, this states legalize marijuana, if they believe that marijuana should be legalized, right? And you have a no and yes for the student. And then across the columns right here, this will be share the parents' politics. Basically, do they share their parents' political views? And so the probability that the student thinks marijuana should be legalized or they agree with their parents' political views is going to be equal to what? It's going to be equal to the number of students that agree with legalizing marijuana, right? Plus the number that of students that share their parents' political views, right? Minus the number of students that both believe that marijuana should be legalized and they share their parents' political views. And so let's take a look over here. So the total number of students who believe that they should legalize marijuana is 114, right? The total number of students who share their parents' political views is 118. The total number of students who believe in legalizing marijuana and share their parents' political views is 78. So it's going to be 114 plus 118 minus 78 divided by the total, which is 165. And that's how you get that number right there, right? And the reason being is you have that or statement there. So this 114 is going to be the total number of students who believe in legalizing marijuana, right? Legalize marijuana, yes, sum across 114, plus the total number of students who believe that or share their parents' political views, yes, parents' political views, sum down the column, you get 118, minus, right, because of double counting, keep in mind that this number we actually end up counting this number twice in this direction and this direction. So we have to actually subtract off for that. And that's going to be the event that the student both believes in legalizing marijuana and shares their parents' political views. That's 78. Then the total number is going to be 165, right, of students reporting. And that's how you obtain this probability. And the trick there is that or statement. And we can actually place a formula to this. And it's going to be called the general addition rule. So if you have two events A and B, the probability that event A or B can occurs, right? And when I say A or B, it's event A occurs or B occurs or both A and B occurs. That's equal to the probability of A plus the probability of B minus the probability of A and B, right? And the reason being is if the events are not disjoint, then what ends up happening is you will end up double counting the intersection of the events A and B. And that's why you have to subtract off for that, okay? And in general, for disjoint events, right, probability of A and B, right, so if they're mutually exclusive or disjoint events, probability of A and B occurring, right, at the same time is going to be equal to 0. So the above formula basically simplifies. So if it's disjoint, then the probability of A or B is probability of A plus the probability of B. All right, so let's take a look at probability distributions. And basically a probability distribution is going to list all the possible events and the probabilities at which they can occur. So for example, if you look at the probability distribution for the gender of one child, right? So the event could be either male or female. And in this case right there, the probability for each one is 0.5. So if you just choose one single child at random from a given population, then the probability is going to be a half of either being a male or a female. All right, so it's going to list all the possible events and all the probabilities at which they can occur. A couple things here. So what are the rules for probability distributions? The events listed, they actually have to be disjoint, right? So to be able to account for this correctly, you have to have the events being disjoint. Obviously, the probabilities must be between 0 and 1. And the last thing is the sum of the probabilities must total to 1. So in this case over here, right, the event being male and or the event being female, they both have a probability of 0.5, which is clearly between 0 and 1, and the sum of those two together totals to 1. Right, so we keep in mind the events listed have to be disjoint to actually form this probability distribution. Now, the probability distribution for the genders of two kids that are chosen, right? So you could either choose a male and a male, a female and a female, a male and a female, or a female and a male. And the probability for each of those events is going to be 25%. And they are all disjoint right there because you can't choose 2 males and 2 females at the same time, for example. They're disjoint. Likewise, if you cannot choose 2 females and then 1 male and 1 female at the same time. So there are going to be disjoint events, and each of the probabilities being 0.25, sum all the way up to 1. All right, so all the criteria are going to be satisfied. All right, let's take a look at a survey. And let's take 1 minute timed exercise for this one. So in a survey, 52% of respondents said they are Democrats. And what is the probability that a random selected respondent from this sample is a Republican? All right, let's take exactly 1 minute to go through this. All right, so 52% of the respondents are Democrats. What's the probability that a randomly selected respondent from this sample is a Republican? Okay, I'm gonna call time. It's been a minute. All right, let's take a look here. And if you answer D, then you actually answer correctly. So given the information here, you can't calculate it. There's a number of possible reasons, right? Now, A is possible if there's only 2 parties, Republican or Democrat, right? And if you know that there's only 2, then we're going to know the probability of being a Democrat. So then A is possible if that's the case. But that's not going to be the case right there. Some people might not be affiliated with any political party, or they may be affiliated with a party that's different than these 2. It could be like an independent party, Green Party, etc. Right? And if that's the case right there, then C can be possible. However, B is definitely not possible, right? Because then our total probability would be greater than 1 in the sum. So if you're more than 0.48, then 0.52 plus 0.48, or something bigger than 0.48 would actually exceed 1. And that's going to break one of the rules with the probability, with this type of probability distribution. Okay, let's take a look at the sample space and complements. So sample space, what is this exactly? Well, it's just going to be a collection of all the possible outcomes of a given trial, right? So it's a list of all the possible outcomes. So like I said before, when you're doing a probability experiments, you usually know what the outcomes can be. You just don't know that what a randomly chosen one will be. So in this case right here, a couple has 1 kid. What is the sample space for the gender of this kid? And so the sample space right here, well, that kid could be either male or female. So the sample space is male or female. Now, if you randomly choose a kid from the population, right, then it's going to be difficult to figure out if they're a male or female, right away, before you choose them, right? So that's the example of the randomness. So we can know the outcomes. We just don't know when and how they're exactly going to occur based on, our choice. Right. So in this case, right, let's keep it simple. 1 kid, sample space is going to consist of either male or female. That's it. So those are the 2 possible outcomes. And if a couple has 2 kids, the sample space of the gender of these kids is going to be either male, male, female, 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 male, or male, female. Right? And that makes sense. And those are all the outcomes right there, right? Those are all the possible outcomes. So if you choose 2 children from the population at random, right there, they're going to be one of these in the sample space, right? So that's where the randomness comes in, because we don't know which one they're going to be, but we at least know all the outcomes. All right, let's take a look at something called a complementary event. So complementary events are interesting. They're basically 2 mutually exclusive events whose probabilities add up to 1, right? So a couple has 1 kid. Well, if you know the kid's not a boy, then we know what the gender of the kid is, because we can eliminate the outcome that the boy is male, right? So it's going to be female in this case. And so in this case right here, boys and girls are complementary outcomes, right? They're disjoint and the probabilities add up to 1. Now let's go look at the 2-kid case. If a couple has 2 kids, and if we know that they are both not girls, what are the possible gender combinations for these kids right here? And so in this case right here, it's going to be male, male, female, male, or male, female, because we know that they're both not girls, right? Okay, so that's going to be the complement right here, right? And I'll show you, actually, you can utilize information of one probability to obtain the other if you have complementary information. And we'll get back to that. We'll come back to that a bit later. Now, 2 processes are independent, right? If knowing the outcome of one doesn't give you any information about the outcome of the other. Okay, so independent in this case. So for example, if you flip a coin, and if you know that you got a head on the first toss, it doesn't give you any information to determining what you're going to get on the second toss, right? So the outcomes of the 2 tosses of a coin are independent, right? And that's what ends up happening right here. So knowing the outcome of one doesn't provide any useful information for the outcome of the other. So that's the coin flip problem right there. So each subsequent flip is independent of the previous ones. Right. This is an interesting one. Now let's take a look here. So this is a fun one. The card one, you have to put a little bit more thought into it. And you have to think about if you're going to replace the card after drawing, meaning put it back in the deck or not, right? So knowing the first card drawn from a deck is an ace, it does provide useful information, right, for getting the probability of drawing an ace in the second draw, okay? And that really depends, right? So it really depends if you do a replacement or not. So if you draw an ace and you don't replace it, right, that's going to actually change the outcomes from the second draw, right? So outcomes of 2 draws from a deck of cards without replacement, meaning you don't put them back. So you pull one card, take a look at it, don't put it back, and then pull the second card right there, right? They're actually dependent on each other, because if you don't replace, meaning you don't put them back, drawing the second card, right, its outcome depends on what you drew for the first card, right? So those 2 events are not going to be independent. Okay, and I think at this point, this will be a good stopping place. And I want to do a little bit of practice when we meet during the live session. Thank you.